Hello everybody, this video is going to be a review of some of the things you learned in Honors Chem related to thermochemistry, and going to toss in a little bit of new stuff related to thermochem as well. Reminder, when we do our notes in this class, you should have a big, bold, obvious title. The title for this would be N2, a quick review. We should also add our target in red pen underneath our title. The targets are in the PDF of the lecture. They're also linked on the table of contents for your notebook. So you can find all the targets in one place if you missed any. Before I begin, I want to give a reminder about note-taking. There's going to be way more words on these slides than you should be writing in your notebook. One of the things that you may notice that's a little different between my AP lectures and my Honors Chem lectures is that there's going to be a lot more text on the slides for these AP Chem lectures. One of the reasons for that is because becoming more familiar with the official definitions and phrasing of some of these topics is important, and that's always going to be a little bit more word heavy than when I paraphrase a definition like I do in Honors Chem. The other reason is that in AP Chem, you are going to be going back to the lectures repeatedly over the course of the year. We use everything so often that you're going to be coming back to them a lot when you do your studying. So you are going to see a little bit more text on these slides. You cannot copy everything down during the lecture. What I like to say is that you are a note taker. You are not a photocopy machine. If I wanted you to have something verbatim, or I wanted you to have it exactly every single thing written down, I would print it for you. That's why we have reference sheets. That's why we have glue-ins. Remember that what we're trying to do here is activate our brain and capture key ideas and things to use when we're studying. If you want more details, open the PDF, add it during your annotations that night, add it while you study, add some extra annotations, read through the PDF as a study tool later on before a quiz, but do not copy everything down. Very, very important. Some of the reminders about the requirements for our notes: big, bold, obvious title, our target in red pen. This is a big deal to me. I will be on you about this all the time. Do not squish your notes. Do not write everything. We need visual gaps between ideas. You need to add annotations in 3 different colors afterwards. I did not just randomly come up with the number 3. Something about our brain responds to seeing 3 different colors on a piece of paper. So you need to be using 3 different colors. You are not just highlighting everything. You should use a little bit of highlighting, sure. You could use color coding, but you should have annotations, which are little notes to yourself, reminders, tips, things like that. You will add KCQ boxes at the end of the notes. K stands for key terms. You do not have to write the definitions, just write the words. Might be a phrase, could be an equation, not always a single vocab word. The connection box is supposed to be a place where you write a very specific connection to something you already know from either another class, something you saw in a movie, something you read about once, something from real life. The idea is to cause your brain to make a connection to a different memory. The question box, you're going to write 2 questions. One can be simple, one can be, what is the definition of this, right? Something simple, but one of them needs to be higher level. That means it needs to be a question that asks you to think about information, maybe compare and contrast something. Maybe it asks you to apply it to a different situation, but it does need to be a little bit more complex than just a simple definition question. You do not have to answer them. They have found that the benefit comes from writing the question. One of the things I like to challenge you with is tell you, why don't you try to write down 2 questions that you think I would put on a quiz or a test. Your ability to make predictions about what's important enough for me to put on a quiz shows that you really understand the material. The other thing you're going to do is once you finish your KCQ boxes, you're going to take a highlighter and you're going to draw a line all the way across the page to separate the notes from your new assignment. Now that we've got all these reminders, let's get started. So, very common for me to do the first lecture of a chapter as a review of honors chem. And you gotta understand that if you're not comfortable, fast, proficient, good at these topics, you're gonna have to go back and do a little bit of extra work on your own. So you can see here I have some silly memes. I love memes. You'll see me add them to everything. And it's important you get the idea here is that we don't have the luxury to forget stuff. It'd be great, it'd be nice, not gonna happen here. Gotta remember everything, okay? Here you can see some of the big things we learned in Honors Chem. We learned about specific heat. We learned how to do MCAT calculations. Depending on the year and depending on who your teacher was, you should have learned a little bit about molar heat, which is the same type of thing as specific heat, but instead of using grams, we would use moles. We learned about endothermic and exothermic reactions. We learned about drawing reaction diagrams for each. One of them starts lower and ends higher. One starts higher, ends lower. We learned how to do calorimetry calculations, where the energy absorbed by one substance is equal to the energy released by the other substance. Very helpful tool to be able to solve for things you wouldn't normally be able to measure directly. We did heating curve calculations for things like phase changes when we're melting or boiling or freezing, condensing. We learned that you have to alternate between MCAT and ML. If those don't feel familiar to you, you pause this video and you go back to the Honors tab and you do a little bit of review. Okay. So, energy is a very big, broad category. A very simplistic way to describe energy is the capacity to do work. And during the course of this class, we're going to look at various types of energy. We could have energy from motion, which is called kinetic energy. How fast are things going? Thermal energy. Is it hot? Is it cold? Potential energy. In physics, they deal with the position of objects a lot. Like, are you at the bottom of a ladder or the top of a ladder? In this class, it will be a lot about the substances that you have. Which chemical formulas do you have? And then the chemical energy, when we do a reaction, how much energy is associated with the substances you're using. So a variety of things that all fall under the umbrella of energy. Thermochemistry has to do with thermal energy. Here are some various forms: electrical energy, light energy, a little bit of nuclear. We don't do much with that in AP Chem, unfortunately. But you can see how all of these types of energy can somehow show up in a chemistry class. We don't often need to calculate the kinetic energy, but we do cover it. Technically, it is something AP Chem might be able to ask you. I don't feel like they do it very often, but they do it just often enough that we should make sure we know how to do it. So the kinetic energy is going to be 1/2 mv squared. So that's probably the first new equation for the AP Chem year, is the equation for kinetic energy. Our mass is in kilograms, typically. Velocity in meters per second. So if you look at this equation, we're going to have kilograms times meters per second squared. And that's what our unit looks like. One of the things you'll need to get comfortable with in AP Chem is that as we do more complex things, our units get stranger and stranger. We're often manipulating our units. The units can really help you remember how to do things as well. Now, this is kind of cumbersome. So the other thing that tends to happen is we take these nasty derived units that look awful and we give them a new name so that we don't have to write it every time. So a kilogram meter squared per second squared is the same as something called a joule of energy, which you've already learned about. And that's the amount of energy it takes to move a kilogram mass object at a speed of a meter per second. Now let's connect this to temperature. People have a tendency to get confused about the difference between the energy involved and the temperature. Temperature is something we measure. You can see this graph. We have a cold sample and a warm sample. And what you should notice is that we have a variety of temperature or variety of energies at each temperature, don't we? They're not all going the same speed. We have a distribution. So what temperature is measuring is the average energy. So in a warm object, we have a higher average kinetic energy. Do you see here the peak where the most number of molecules are going? They're going this fast compared to the peak over here. On average, more molecules are going faster in the warmer sample. It's very important, that word average. AP Chem loves to ding people on not mentioning that there's this distribution, that it is an average. So, law of conservation of energy, which is first law of thermodynamics. We cannot create or destroy energy. You're probably familiar with that concept from Honors Chem, and now you know it's called the first law of thermodynamics. What we're allowed to do is transfer energy, or we can convert it from one form to another. But whatever your energy is when you start needs to be the same at the end. The implication of this is functionally that we can't do magic, okay? You can't come up with some system that produces energy indefinitely. If we could, we wouldn't have all the energy problems we have these days, right? With gas prices being crazy and trying to design things like solar panels. And, the problem is that the energy is constant. So we have to play games to convert energy into different forms. We can't just magically produce more and more and more. The most common conversion that we talk about is going from potential energy to kinetic energy. Physics deals a lot with that as well. One of the reasons why this first law of thermodynamics is so important is that it's very convenient. It allows us to be very creative with how we measure things and the calculations we can perform. You learned when we did calorimetry that it's difficult, for example, to put your thermometer inside a metal block, right? You can't get that thermometer inside a solid object. So what we do instead is we measure indirectly. You can put your thermometer in a cup of water. That's easy. So you can measure the water instead of the metal block. And you can exploit the fact that the energy absorbed by the water was equal to the amount of energy that was released by the metal block. So this concept of manipulating the first law of thermodynamics is really important. One of the reasons people struggle with this is because they mix up the concept of system and surroundings. The system is whatever thing we're actually interested in. Is it the chemicals? Is it the metal block? What is the actual thing that we're trying to study? And the surroundings is everything else. What we are often looking at in something like calorimetry is that exchange between system and surroundings. If the system is the metal block, the surroundings was the water. So when we have this energy exchange, one option is that it's endothermic. In an endothermic reaction, the system is absorbing energy, the surroundings are releasing energy. So the system is gaining energy, the surroundings is releasing, it's decreasing. Q is positive for the system and negative for the surroundings. One of the things that's hard for people is thinking about real life examples. Because for an endothermic reaction, if you reach out and touch the beaker, if you reach out and touch the container, if you look at your thermometer, you're going to see it get colder. And that feels backwards. People say, but it's absorbing energy. How can it be feeling cold to us? Why is my temperature going down? That's because what we feel and what our temperature, what our thermometer is reading is the surroundings. The thermometer is in the water, and the water is not the system. The water is the surroundings. When we grab the beaker and it feels cold, it's because the heat is being taken out of our hand. It's being taken out of the air. It's being taken out of the water. The system, the chemicals, those bonds and all that themselves is endothermic. But what I touch and what my thermometer shows is the temperature going down. Because it's stealing heat out of my hand. It's stealing heat out of the surroundings. We measure the surroundings. We're not often measuring the system directly because it's too hard. You should be familiar with graphs like this. You can see, look, endothermic, it absorbed energy. Drawing pictures like this where your arrows point in the direction of absorption can be helpful. Heat is being absorbed into the chemicals, which means everything on this outside should feel cold. The opposite would be exothermic. The system releases energy, the surroundings gain it. The system energy decreases, surroundings increase. System is negative this time, surroundings are positive this time. So if I reach out and grab the beaker this time, I'm going to feel hot. My thermometer is going to go up. Sometimes it could be so extreme that you see flames, right? That's exothermic. Flames are being released. It's that hot. Oops. There we go. So we can see here on our reaction diagram, we're going to end lower than we started. And our arrows this time are showing you that heat is being released outward. If I were to grab out here, it would feel hot. Like I mentioned earlier, calorimetry is one of the best examples of this. We are measuring indirectly. And usually, water will be our surroundings. Just a couple of unit things that can be helpful. Calorie is not often used in chemistry, but it is more used in real life or in biology sometimes. A calorie is the same as the amount of energy to raise 1 gram of water by 1 degree Celsius. If you ever go by something like a propane tank, maybe you have like a fire pit or a barbecue, you may see BTU. BTU is the energy for 1 pound of water to change by 1 degree Fahrenheit. Just a couple little facts maybe to jot down in case you come across a problem that uses those. Now, one thing we have to think about is the process of heat transfer. Heat transfers, things heat up because particles are colliding. This is probably something you didn't learn in Honors Chem, one of those little new aspects to the topic. So we have something that is higher temperature, which means the particles are moving faster. Do you see we have these big arrows? This one's going really fast. It's going to hit something that is colder. You see this one is small. Some of that energy will be transferred, and now look, this particle is moving faster, and this one slows down a little bit. It is important that you understand that the energy is being transferred from the hot object to the cold object. Things speed up. We're always speeding up that lower temperature thing. It would be better to say, oh, I put some ice into my drink. The ice is heating up. That would be better than saying my drink is cooling down. And it's all because of those particles hitting. AP Chem loves to come up with scenarios where you have to think about the physical collisions of the molecules. We want to remember that these are particles that are colliding. Eventually, if you leave it long enough, we will reach what is called thermal equilibrium. At that point, the average kinetic energy will be the same for both substances, which means the temperatures are the same. Do you see here I put the word average? Remember, we have to say average kinetic energy. So when we're doing calorimetry, if you remember, our T final for both substances, the metal block and the cup of water, would be the same. Really important. Now, in most Honors Chem classes, you use styrofoam cups to be your calorimeter, or maybe you buy a little bit more fancy calorimeter. The fanciest would be what's called a bomb calorimeter. We do not have one of these. These are useful though because the volume is going to be maintained. It's going to stay the same. One thing that comes into play here is the heat capacity of the actual calorimeter. The calorimeter itself can absorb energy. And so you have to know how much energy it will absorb so you can take that into account of your calculations. One of your labs is going to ask you to figure out how to come up with that calorimeter constant. You'll research on the internet and find a procedure for how to do that. You'll notice here that the calorimeter constant does not have mass, because we're just taking this as like an object in its entirety. We don't change the mass of the calorimeter. So instead of using Q equals MCAT, it just turns into Q equals cat. Right? There's no mass component here. But usually in real life, in our high school level, we're using a coffee cup. We're using that styrofoam because it's very, very insulating. In a perfect world, you would have several cups stacked together. The little air gap in between is extra insulation so that the heat can't leave the container as easily. And you would have a lid on top so that heat can't escape out the top. One thing that we're going to learn in this class that we're going to start using more often is something called a state function. The reason why this is an important concept is because energy is a state function. A person standing on the top of Mount Everest is going to possess the same amount of potential energy regardless of how they got to the top of the mountain. If they were dropped from a helicopter and they parachuted down here versus they climbed all the way to the top, at the end, wherever they're standing, if they're both standing at the top, they would possess the same amount of potential energy. Now, clearly, one of those methods is going to take a lot more effort. Work, the amount of work it took to get there, is different. We have a tendency to say, oh, that took more energy. That took a lot more energy, when what we really mean is it took more work. I like to say that by the end of the year, you've all finished AP Chem. You're all at the top of Mount Everest. Some of you had to put in more work to get there than others, but we've all reached the final position, which is the same. So, same kind of idea here. Another state function would be the elevation change. If everybody started at the bottom and went to the top, their change in elevation is the same. But the time it took there would be different. The straight path probably went faster than the long zigzaggy path. So there's some common examples in daily life. Think about that when you go on a hike, right? Oh, your elevation changes a state function, but the time is not. Now, the rest of this PowerPoint is a series of practice problems with a little bit more reminders tossed in. It's going to go over specific heat, latent heats, molar heats, calorimetry. I gave you a glue-in that has the practice problems on there. My suggestion would be to pause the video, try the practice problems, and then unpause and see if you got them correct. I'm going to go through and I'm going to give some commentary. I'm going to walk you through how to do all the problems. If you got it wrong, you may want to watch that section of the video. It is required that everybody do the practice problems, but you personally may not have to watch the second half of this video. If you do, you got to make a mature choice and do it. Okay, put the time in that you need personally to do well in this class. Okay, so why don't you find your glue-in, pause the video, get a calculator, get all set up, and when you're ready to do those practice problems, get started. All right, so for specific heat, it is the measure of a substance's intrinsic ability to absorb heat. Based on the material, how much heat can be absorbed. Specific heat is the amount of heat it takes to raise the temperature of 1 gram of the substance by 1 degree Celsius. So you can see here, it takes 0.128 joules of energy to get 1 gram of lead to go up by 1 degree Celsius. If you look down here, look at water, look how big that is. Water can absorb a lot of energy before the temperature goes up. That's why it takes so long to boil water. It just absorbs and absorbs and absorbs, and the temperature doesn't change very quickly. Molar heat capacity would be the energy to raise 1 mole of substance by 1 degree Celsius. We would functionally do things the same, we just would be using mole values instead of grams. We have our MCAT equation. One thing that will pop up often in this class is that some people, like me, prefer to take the normal equation and put all my numbers in and then rearrange it. Some people prefer to rearrange the equation first and then plug your numbers in. It does not matter. Does not matter. So you should remember Q is the energy, C is mass, specific heat, and change in temperature. You will often see a capital Q. Totally fine. I use the capital because my lowercase q's look the same as a G and it confuses people, so I use capitals, but lowercase is typical. So question number 1. I love this question because this requires you not to do a calculation, but instead to think about what specific heat really means. So we give identical amounts of heat to 50-gram blocks of various materials. They all start at 25. We want to know which block is going to have the largest increase in temperature. Which one's going to heat up the most? We give it the same amount of energy. They have the same mass. They start at the same temperature, but they're not all going to end at the same temperature. Which one's going to heat up the most? Pause the video and think about it. All right, the one that will have the largest increase in temperature is lead. So what we have to do is we need to think about our MCAT equation. And what are we actually solving for conceptually? We're solving for delta T. So rearrange your delta T, and you will see that the smaller your C value, the larger your delta T gets. Dividing by a small number gives you a bigger answer. If Q is the same and M is the same, the only part left is specific heat. Look at the specific heat for lead versus silver versus copper. Lead has the smallest. So the smallest specific heat will give you the largest temperature change. Lead cannot absorb very much heat before the temperature goes up. Copper can absorb more heat before the temperature goes up. People often wonder, how does it absorb the heat? Where does the heat go? If they're not moving faster, if my temperature is not going up, where's all the energy going? And you have to remember that molecules don't just move faster side to side. They might vibrate more, right? They may rotate around faster. There's other ways they can absorb that energy besides just moving side to side faster. All right, let's move on to heating curves. Remember, we have to do our calculations in segments. When we heat something up or cool it down, we can use MCAT. But if we are going through a phase change, there is no change in temperature. All of the energy is being converted into that potential energy because things are getting spread further apart. So we use a slightly different equation. We're going to not use MCAT, we're going to use ML. We know energy is still being put into the system or removed. So we can't have a delta T of 0. We have to have a slightly different equation, ML. You should have all your numbers memorized. If not, get those memorized. Remember that in a heating-cooling problem, MCAT, the positive or negative symbol is being applied from the temperature change. But in an ML equation, we have to manually supply the positive or negative sign onto our latent heats. So our latent heat of fusion would be positive if you were melting, and it would be negative if you were freezing. So why don't you give this one a try? You're going to go from ice at -6 to steam at 100. You're going to have to do many sections of that curve. Pause and give it a try. All right. Did you get that? How did it go? Let's think about it. So if we have ice at -6, we're going to have to heat it up to 0 degrees using line 1, which is an MCAT equation. Remember that our delta T is only for the line segment that we're on. You don't do your overall delta T. Line 1 does not go to 100. It ends at 0. You may often see me write minus a negative like this. We all know that means positive, right? But people will often forget, wait, where did the positive come from? I thought we were subtracting. So I like to kind of show minus and negative. Then we got to melt it. Then we have to heat the water up to 100. And then we have to vaporize it into steam. We don't have liquid water at 100. We have steam at 100. Then our Q total will be the sum of all of those numbers. One thing that you will also have to get used to is going back and forth seamlessly from things like joules to kilojoules. We do it all the time. Grams and kilograms. Get comfortable going back and forth. You could have also written this answer. You could have written this in scientific notation, or you could convert it to kilojoules. Up to you, unless the problem asks for a specific unit. All right, next let's do a molar heat. We will use NCAT, N for moles. So pause the video and give this one a try. All right, we're told what the temperature change is. We're told what the Q value was. We know the molar heat capacity, so we're just solving for moles. I like to plug my numbers in and then I rearrange. And I find that N is 0.84 moles. I hope you can see that these problems are not very different. It's just using moles instead of grams. All right, on to calorimetry. I think calorimetry is a test of your math abilities. I think that's the big deal here, is your algebra skill. All right, on to calorimetry, where we're going to indirectly determine the energy that's being transferred. So for example, very common type of problem is a hot piece of metal added to cold water. Energy is being transferred from the hot piece of metal to the colder water. The actual change in temperature will depend on how much metal you have, how much water you have, and what the specific heats of those substances are. The metal will be losing energy and the water will be gaining it. What I like to do is think of the plus and minus as equal but opposite signs. Algebraically, it really doesn't matter which side you put the plus and minus. You're going to be rearranging stuff anyways. Negative implies exothermic, positive endothermic, so that's why we typically would put them how you see here. But algebraically, it doesn't matter because it's actually an opposite sign. So if Q is the same as MCAT, what we can do, instead of saying Q equals Q, is we can say MCAT equals MCAT. We have negative MCAT equals MCAT. The metals are cooling down and the waters are heating up. That way you can plug in your masses, you can plug in specific heats, you can plug in starting temperatures and find ending temperatures, or maybe you know the delta T and you're solving for a specific heat of metal. It allows you to solve for a variety of things. So give this one a try. Pause the video so you can give it a try on your own. All right, here we're solving for delta T. We have hot iron being put into cold water, and the temperature of the metal is going to decrease by 10. The water is not going to increase by 10 degrees. That's a very common misconception. The water temperature is only going to go up a little bit. The water will absorb most of the energy, so we will not see a big temperature change. You can see that the metal cooled down by 10, but the water only heated up by 1.5. That is one of the really good things about our planet being mostly water-based. So there's a lot of water to absorb all the energy we're putting out there. That way our temperature doesn't change as much as it would otherwise. So we're going to say Q equals negative Q. MCAT equals negative MCAT. I had 500 grams of water, specific heat of water. I don't know the temperature change for water. I know that we're going to be releasing energy from the metal. We have 700 grams of it. Specific heat is told to us, or you could look it up on a chart. And I know that it's going to decrease by 10 degrees. Do you see how those negatives cancel out? Be careful for double negatives. And we have our final temperature change. All right, one more practice problem. Good for you, you've hung in there, hopefully. This is a little different. We're mixing 2 cups of water together, aren't we? It doesn't matter. It's still substance number 1 and substance number 2. One of them is going to cool down and one of them is going to heat up. It doesn't matter. All right, before I show you the answer, I want to give you something to think about. If we're starting at 22 degrees and 36 degrees, we're not going to end exactly halfway because we don't have equal masses. We have more water at 36 degrees, so our final temperature will be closer to 36. We also can't end below 22, and we can't end higher than 36. So answer choice 42 is gone, right? And I'm pretty suspicious about 29 because that's closer to 22 than 36, right? So I can use some common sense on my answer choices. When you're all done, you should end up with 32 degrees. Which meets these criteria, doesn't it? So water number 1 equals negative water number 2. MCAT equals negative MCAT. I had 50 grams of water 1. I had 125 grams of water 2. Now, what do you notice about your specific heats? They're the same because it's the same material, which is nice because it makes your algebra easier. People seem to think water plus water problems are more complicated, but they're really easier. Don't let it trip you up that it's different than the physical lab you've done of metal block into water. It is still calorimetry. And you get your final answer. All right, everybody. I know that was lengthy, but hopefully you can see that I wanted to review some of the things from Honors Chem, but add in a little more detail here and there to some of the concepts, which is that AP level, understanding them on a deeper level. So that is it for this video. Make sure you go and add your KCQ boxes. Make sure you go back and add your annotations in 3 different colors. Really help your brain remember and recall this information. All right, everybody, that is it. I hope that was helpful. Bye.